Hello, my name is Taylor Forbush.
And I'm Joe Savage. We did our analysis on bridge trusses.
After some research, we found out that there are so many more geometries for bridges than what we had realized. Here are a majority of the truss geometries used in bridges today. We settled on the analysis of 3 of the more popular truss designs. These are Warren Pony, Warren Through, and Pratt Through. And here are some examples of each of them in real life.
For our initial conditions, we used a yield stress of 30,000 psi and a factor of safety of 2. We tested each of these scenarios up to the yield stress of the bridges for 3 different meshes: coarse, medium, and fine. The geometries were drawn in NX 10.0 and later imported into ANSYS for finite element analysis. We fixed the base of the support legs in all directions as well as the edge of the road. We applied 2 different forces to each of the 3 designs: a downward force on the surface of the road representing the weight of the bridge can hold, as well as a horizontal force against the side of the truss. This represents the bridge's resistance to strong winds. We then combined the maximum forces and found the maximum von Mises stress.
Before analysis, we expected the Warren Pony to be the weakest of the 3 under our conditions, and then the Warren Through, and lastly, we believed that the Pratt Through would be able to withstand the highest forces with the least effect.
It should be noted that the coarse and medium meshes were large enough that they span the width of the truss members. This means that the force was constant across the trusses and likely resulted in inaccurate stress measurements. The fine mesh, however, was small enough to fit inside the width of the truss and allowed for accurate stress measurement. You can see that the stresses are more concentrated in the Warren Pony than the Pratt Through or the Warren Through. This is likely due to the lack of additional vertical supports throughout the structure. This is part of the reason why we chose it as the worst performing.
We summarized our results in a couple of tables in order to accurately compare the outcomes and make our conclusions. The first table contains the forces each bridge geometry was able to withstand before reaching the yield stress. This was first analyzed for each force individually. We then combined the forces and found the resulting maximum von Mises stresses and deformations for each geometry.
The results showed that the Pratt Through could withstand the most force both down on the surface of the road and across the truss, whereas the Warren Pony withstood the least amount of force in both directions and had stress levels in between that of the Pratt Through and the Warren Through. The force down on the road was most significant in the Pratt Through, and it exhibited by far the least stress and smallest deformations under its maximum conditions. This allowed us to conclude that it is the preferred truss structure of the 3 that we analyzed, and confirmed our initial expectations.
We took our Pratt Through bridge to the real world to see how much our maximum force is really equivalent to. We discovered the bridge could hold 10 minivans at 6,000 pounds each, 8 full-size trucks at 10,000 pounds each, 3 beverage trucks at 26,000 pounds each, 4 city transit buses at 33,000 pounds each, and a cement truck and a sleeper cab, both in excess of 33,000 pounds before yielding. This is in fact quite a bit more than what could physically fit on these bridges, making this load bearing quite impressive. Thank you.